All hurricanes start off as tropical disturbances, areas of disturbed weather that can result from things like troughs sliding into the tropics, waves developing along frontal zones over the ocean, etc. Most Atlantic hurricanes start off as what we call easterly waves. Easterly waves are inverted troughs that move from east to west. So a typical trough, one that might induce severe weather across the US, as we know, is a downward kink in the height contours aloft. Now, the winds in the mid-latitudes here in the US flow from west to east. So those height contours are, again, it's a downward kink in the height contour. So you get that kind of counterclockwise rotation, counterclockwise circulation in the winds associated with that trough. An inverted trough is just the opposite of that. It is a trough that's basically upside down. So here in the tropics, the winds flow from east to west. An inverted trough is just an upward kink in the height contours. And again, remember that the winds are going from east to west. So you're still getting that kind of counterclockwise rotation in the winds. And so this is still considered a trough. It's just flipped upside down from what we would consider a normal trough here in the mid-latitudes. It's an inverted trough. Typically, these easterly waves develop as thunderstorm complexes in western Africa. These complexes eventually dissipate. The area of disturbed flow aloft moves over the Atlantic. Initially dissipates because of the cooler waters here along the western coast of Africa. But once they get toward the warmer waters of the open Atlantic, they start to intensify again, and thunderstorms develop. Of course, these easterly waves are troughs. They're sources of lift, and with an unstable atmosphere due to the warm ocean waters of the open Atlantic, thunderstorms start to develop. Now, as these thunderstorms start to develop, they release what's called latent heat. Latent heat is just the energy that's released due to phase change. And in this case, it is the evaporation of all this warm water over the Atlantic that can fuel more and more thunderstorm development. It creates a cycle. Thunderstorms develop, more and more latent heat is released, and more thunderstorms develop. As this happens, the pressures start to lower in that area, and you get an area of low pressure that develops as the thunderstorm coverage increases. The Coriolis force, which is due to the rotation of the Earth, allows the storms to rotate around the center of low pressure in a counterclockwise fashion. And as the pressures continue to deepen, you can get a tropical depression, and eventually a tropical storm, and eventually a hurricane, if the ingredients are there for hurricane maturation.
Have you ever wanted to spend a full week chasing storms? We're opening up seats for another 2027 tour after our previous 2 rounds sold out almost immediately. You'll take part in daily forecast discussions, target selection, and the real-time decisions that shape every chase day. Seats are limited, and this tour is priced to make an unforgettable storm chasing experience more accessible. Click the link in the description below to reserve your seat before it sells out.
Now, what are these ingredients for hurricane formation and maturation? As we've already begun to discuss, we need warm water and a lot of it. Not only do we need sea surface temperatures to be quite warm, generally above about 80 degrees Fahrenheit, but we need those warm temperatures to extend quite a ways down into the ocean. This can be measured through a product called oceanic heat content. This is basically just an integration of the vertical temperature profile of the ocean from the sea surface down to the 26 degree Celsius isotherm, which is about 80 degrees Fahrenheit. So it basically takes into account the total amount of energy available for potential developing tropical systems. The higher the sea surface temperatures and the greater the oceanic heat content, the greater the reservoir of fuel available to any developing tropical systems is. And that the higher these values are, the better the chances are for hurricane formation and maturation. Remember that hurricanes are fueled by the latent heat release of evaporation from the ocean surface. So if you don't have those high evaporation rates that come from warmer waters, you're not going to have a very favorable environment for that latent heat release and therefore the formation and maturation of a hurricane. So again, you need lots of warm water at the surface, but also extending down well into the ocean. The higher the oceanic heat content, the higher your sea surface temperatures are, the greater the chances are for hurricane development. Related to this is a moist atmosphere. If you have lots of warm water, you're going to get a lot of that evaporation of those warm waters into the air, providing a lot of water vapor to the air and a deep layer of moisture in the atmosphere for the these thunderstorms to feed off of. If you have, again, cold waters, or if you have some dry air intruding into the potential area of development aloft, that's going to thwart robust thunderstorm development around that developing low pressure center, and it's not going to be as favorable for hurricane development. Similarly, you need a very unstable atmosphere. If you have a lot of colder ocean waters, that's going to lead to quite a stable low-level air mass and inhibit thunderstorm development. But if you have warmer waters, that's going to lead to a much more unstable environment and a favorable one for hurricane formation. Finally, contrary to supercells and tornadoes, hurricanes need weak vertical wind shear, which is that change in wind speed and direction with height, to intensify. This might seem a little counterintuitive. We have a rotating storm system. Wouldn't you need wind shear for the storm system to rotate? That's not the case. Let me tell you why. Mid-latitude cyclones, which are low-pressure systems that cause severe weather across the world, here in the United States as well, those are usually tilted with height. So the center of low pressure at the surface is going to be offset from the subsequent levels as you go up in the atmosphere. It's kind of usually tilted back toward the west or northwest just a little bit. Hurricanes are vertically stacked systems, so the center of low pressure at the surface should be right below the center of low pressure at the subsequent levels of the atmosphere as you go up. It is, again, vertically stacked. Hurricanes need to be vertically stacked in order to intensify. Wind shear, whether it is the change in direction of the winds with height or increasing speed with height, that is going to cause a tilt in the system. And a tilted hurricane or tilted tropical cyclone is not a system that is going to be able to intensify as effectively as if it were vertically stacked. So vertical wind shear is a big no-no for hurricane formation. Tropical systems need very weak vertical wind shear in order to intensify. All right, now let's talk about what governs the movement of hurricanes. Hurricanes are self-propagating systems, meaning that just like supercells can persist for quite a while based on the dynamics within the storm and the dynamics surrounding the storm, hurricanes can do the same thing. It's that constant cycle of latent heat release via evaporation off the warm ocean waters that allows a hurricane to propagate for really an extended period of time until that warm water source is negated or there's some other environmental factor that impedes the progress of the hurricane. But the overall background pattern is what guides the actual movement and motion of hurricanes. And specifically, it's the winds in the mid and upper levels of the atmosphere, really 500 millibars and above, that dictate the motion of hurricanes. So that means that the locations of troughs and ridges are quite important in steering hurricanes. In general, over the Atlantic, we have a feature called the Bermuda High, which is a big ridge of high pressure, really a fairly permanent ridge of high pressure that is situated over the open Atlantic that tends to guide hurricanes and developing tropical systems to the west out over the open Atlantic, really especially those waves that come off of Africa and even the storms that develop in the Caribbean. They're going to try to drift west around the base of this Bermuda High. And then as they reach the western side, those winds turn out of the south aloft, and that is going to usually try to help them turn toward the north, and that's why we get quite a few landfalls here on the Gulf Coast, the east coast of the U.S., around the edge of that Bermuda High. That also means the strength of the Bermuda High is a critical factor in determining where that northward turn is going to take place. So a stronger Bermuda High, going to be a ridge that extends farther off to the west, generally into the Gulf perhaps, that's going to lead to hurricanes traveling more to the west longer before they make that northward turn. Whereas a weaker Bermuda High, not going to be not going to jut out as far to the west, it's going to mean a sooner northward turn around the western edge of that high. So the Bermuda High is pretty critical in steering hurricanes out over the open Atlantic. Now, smaller scale troughs and ridges, especially those across the United States and near the United States, can really determine the path that hurricanes take as they near the U.S. coast. Here's an example from 2020 of Hurricane Hanna that impacted portions of far south Texas. Here is our 500 millibar chart as the hurricane was developing. Here is the start of the hurricane, that closed contour right there over the Gulf. And so let's talk about our steering currents here. We have a big ridge over much of the U.S., very expansive ridge here. The center of that ridge looks to be somewhere over Oklahoma. Very calm winds there in eastern Oklahoma, southerly winds on the west side, northeasterly winds on the east side, more easterly flow on the south side, westerly flow on the north side. So our center of high pressure looks to be right there in that Oklahoma area. So south of that, where the hurricane was going to travel, we have very light easterly winds, about 5 to 10 knots of easterly flow surrounding the hurricane right there. So those would be our general steering currents. We'd expect that the storm would slowly move off to the west, and lo and behold, that's exactly what it did. You see there, the hurricane starts to gain some steam, starts to approach the Texas coast. We retain those steering currents, 10 to 15 knots of flow there, still out of the east surrounding that hurricane, and it continued to move off to the west ever so slowly, eventually making landfall there in far south Texas. How about another example? This is Hurricane Helene from 2024. Here is the hurricane down here across the eastern Gulf. And now we introduce a little bit of a closed low into the equation. So we have a pretty broad ridge of high pressure here over the Atlantic. Unfortunately, the SPC Mesoanalysis Archive doesn't go out far into the Atlantic, but you can pretty clearly see there's a large ridge of high pressure situated over the Atlantic. And then we have this closed low situated here over the kind of Mississippi River, Ohio River valleys. And that kind of creates a pretty clear lane for Helene to travel to the north. You see the background flow out of the south pretty uniformly there between that closed low and the ridge of high pressure. So you'd expect to see that Helene would move pretty quickly, given that this flows about 25 to 30 knots here, pretty quickly toward the north, and that's exactly what it did. Those two features remain there. That ridge stayed pretty steadfast over the Atlantic. The closed low kind of just meandered there across the Mississippi River Valley. And Helene eventually just took that path up into the Big Bend region of Florida, moving with the southerly mean flow. Sometimes it's not that simple, though. This is Hurricane Ian from 2022. Hurricane Ian right there on just inside the bottom right corner of the image. And initially, the steering currents were out of the kind of south-southeast, a ridge over the Atlantic down here that was steering Ian ever slightly toward just west of due north. So south-southeasterly winds. But this trough was a little bit of a wild card. Some of the models were differing on the behavior of this trough and how it would interact with Ian as it moved north. Some had it a little bit more amplified, meaning it would the westerly and southwesterly flow around the base of the trough would start to push Ian off toward the northeast a lot sooner. Some had a little bit less amplified, less intense trough that would allow Ian to move a little bit farther north before taking the turn off to the east, the northeast. So it was a little bit unclear. And these trough situations, when you have an incoming trough that's moving across the U.S. and you have a hurricane coming up from the Gulf or toward the East Coast, it can be quite difficult to really pinpoint the exact track of the hurricane because the trough is handled slightly differently among the models. What happened was Ian continued to move off toward the north, toward the Florida West Coast. The trough continued to dig down a little bit, and as it did so, that again, westerly to southwesterly flow around the base of the trough started to impact Ian ever so slightly, and it started to tug it off toward the northeast as it approached the west coast of Florida, and it eventually went inland. So these troughs are very, very difficult and can throw a wrench into the forecast, the track forecast in particular of hurricanes, and it's very critical to forecast these troughs and their behavior correctly, as that can dictate how soon the hurricane will change its motion, and that can, of course, impact a lot of people, really be very critical for where you need to set up for your hurricane chase. These can be quite difficult situations to forecast. And sometimes the steering currents break down, causing the hurricane to move very, very slowly or even stall out completely. This is Hurricane Harvey from 2017. We all know what happened with Hurricane Harvey. It basically sat there along the southeast Texas coast and dumped 50, 60 plus inches of rain in the Houston metro area. That was because the steering currents broke down. Here is the hurricane just on the bottom portion of the screen there. It was initially being driven by a little bit of a ridge that was centered over the Gulf into the southeast U.S. You see the center of the ridge right there over the open Gulf. So we had south-southeasterly flow that was slowly pushing the storm off toward the north-northwest. But eventually, as it approached the Texas coast, that ridge broke down and the overall steering currents broke down as well, allowing it to just sit there, just meander ever so slowly along the Texas coast. You see as it makes landfall on the Texas coast as a Category 4 hurricane. Really no feature of note driving the motion of the hurricane. No real notable ridges, troughs, or anything. Very, very weak, chaotic flow here at 500 millibars surrounding the storm. Even a little bit of a northerly component to the flow, opposing the northward motion of the storm, just allowing it to really sit there over the Texas coast and dump a bunch of rain along that southeast Texas coast, particularly in the Houston metro area. The same thing happened with Hurricane Sally that made landfall near Gulf Shores, Alabama in September 2020. Here is Hurricane Sally, and you'll notice nothing really going on surrounding the storm. Just very light winds aloft, not really any set, uniform direction of those winds. Just very weak steering currents, allowing the storm to move very slowly, rapidly intensified as it approached the Alabama coast. And you see it's moving very slowly because we just have 5 knots of flow at most there around the hurricane. Not really any feature of note, any ridges or troughs to steer the storm. So it very slowly made its way near the coast there. It just sat offshore for a while before finally coming inland near Gulf Shores. Weaker storms tend to be influenced more by the trade winds, which are out of the east, and they tend to travel more to the west a lot longer than stronger storms, which tend to move more poleward. So as more rapidly a tropical cyclone develops into a tropical storm or hurricane, the quicker it takes a little bit more of a poleward or northward turn or motion overall. So that's something to keep in mind often in the development phase of a tropical cyclone. If it remains weaker, that can keep it moving to the west quite a bit longer, but the more rapidly it strengthens, that can allow for a little bit of a meander off to the north a little bit more quickly. Of course, the things that govern hurricane motion the most are really most often those troughs and ridges in the background pattern aloft. But the strength of the hurricane does have something to do with it. Weaker storms tend to move west for longer, influenced more by the easterly trade winds, whereas stronger storms tend to move a little bit more poleward or a little bit more northward in general.
Remember to check out those links in the description below, and then watch another video.